Hello, this is the Theta group, and we are doing neutrino flavors and oscillations. I will talk about what neutrinos are, how they were discovered, and why you should care. Neutrinos are highly relativistic elementary particles with no charge and hardly any mass. They are also spin 1/2 particles. An elementary or fundamental particle is one that cannot be broken down any further, or in other words, is one of the building blocks of our universe. Neutrinos are known to come in 3 different flavors. Just like how Liz likes to refer to mathematical objects as beasts, flavors are just a more fun word for types. These flavors are identified by the particles that are produced when the neutrinos interact. Electron neutrinos produce electrons when they interact, muon neutrinos produce muons when they interact, and tau neutrinos produce tauons when they interact. If you haven't heard of muons and tauons, they are basically just larger electrons. Those 3 particles and their corresponding neutrinos are collectively referred to as leptons, and for each lepton, there also exists a corresponding anti-lepton, represented with a bar. The details of the antineutrinos are a topic for another video, and for now can be just considered the same as the neutrinos. Anti-electrons, anti-muons, and anti-tauons can be just considered oppositely charged counterparts. You will also soon find out from Do that there is another way to classify the neutrinos. Because the types I have just defined are classified by their interactions, they are called interacting neutrinos. Now, to clarify what I meant earlier by neutrinos having hardly any mass, let me start with saying it's complicated. As it turns out, neutrinos have no well-defined mass. Rather, they are in a quantum superposition of 3 masses, much like the particles we have studied are in a spin superposition. Unlike with spin, however, we do not know the absolute masses associated with neutrinos. We do, however, have some information. It is known that the sum of those 3 masses is less than 1/millionth of the mass of an electron. We know the difference of the squares of the masses. Lastly, we know an upper limit on the mass of an electron neutrino, which, as of 2022, is 0.8 electron volts per c squared, or about 1.5 times 10 to the negative 36 kilograms, with 90% confidence level. Neutrinos are so light that they were actually originally believed to be massless. On top of having no charge and being nearly massless, neutrinos do not interact with light, making them invisible. So how did somebody discover an invisible, nearly massless particle that doesn't interact with the electromagnetic force or even the strong force? It started with the beta decay problem. In the most basic case, a free neutron will decay to a proton and an electron. However, if this were all that was to it, then both conservation of energy and conservation of angular momentum would be violated. Hence, Wolfgang Pauli postulated the existence of the neutrino as a 3rd particle involved in nuclear beta decay, as shown here. Being more specific as to who to give credit to, Wolfgang Pauli is credited with postulating the existence of the particle, Enrico Fermi is credited with naming the particle the neutrino, which stands for little neutral thing, and Fred Reynes is credited with the discovery of the neutrino. Now, why should you care about neutrinos? Well, for one, they are the most abundant particle with mass in the universe. It is estimated that about 100 trillion neutrinos pass through our body every second. Neutrinos are produced by our own bodies and by things all around us, such as bananas even. Through the decay process of potassium-40, bananas produce over 1 million electron neutrinos every day. Some of the applications of neutrinos include carbon dating, which uses beta decay, and the detection of nuclear reactors and supernovas. Additionally, neutrino detectors in the sea are currently being used to study marine life. There are still many mysteries surrounding neutrinos, so many of their applications may not yet be discovered. 2 of these mysteries are whether there are more than 3 neutrino flavors and the exact masses associated with the neutrinos. Now you will hear from Do, who will explain some of the quantum behavior of neutrinos.
Neutrinos are weird. We've already established that neutrinos have nearly no mass, travel at almost the speed of light, and don't interact with photons, making them invisible to direct optical detection. For fun, we've even decided to categorize them by flavor, as if they were ice cream. However, neutrinos have another very weird property, that their identity changes. While an electron is an electron no matter where it is or how it moves, whether it's around an atom or flying through space, it has the same charge, the same mass, and it simply is an electron. But neutrinos are different. They're quirky, and they're not like the other girls. Instead, their identity changes depending on the interactions with other particles and as they move through space. To illustrate, we will look at some of the real-life phenomena that provided evidence to the non-constant identity of neutrinos. First is the solar neutrino problem. Let's look again at nuclear beta decay. We understand that the decay of protons into a neutron, positron, and an electron neutrino is part of the thermonuclear reaction chain in stars like our Sun, meaning that we should be constantly bombarded by neutrinos. However, in the 1960s, scientists discovered that the number of neutrinos detected was a third of the number that models suggested it should be. Solutions proposing that the temperature or the pressure of the Sun failed to hold up to observed data, so the problem went unsolved. In 1985, another problem with neutrinos arose, known as the atmospheric neutrino anomaly. It goes as such. When a cosmic ray proton hits the atmosphere, it produces a pion. This pion then decays into a muon neutrino and a muon, with the muon decaying further into an electron neutrino and another muon neutrino. As such, one would expect double the number of muon neutrinos as there are electron neutrinos. However, the ratio was found to be almost 1-to-1. But how could this be? The answer was found to be neutrino oscillations. We have seen that there exist three types of interacting neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. There also exist three types of traveling neutrinos. However, these aren't a 1-to-1 correspondence. Instead, the traveling neutrinos act as some superposition of the three interacting neutrinos, and, specifically, as one of three mixes. This would answer both the solar neutrino and the atmospheric neutrino issue. Atmospheric muon neutrinos are likely the mixed state V3, as about half of them oscillate to other types of neutrino flavor. The number of expected electron neutrinos from the Sun is 3 times what we found, so the emitted neutrinos must be the mixed state of V1. However, electron neutrinos most likely form as V2, meaning that solar neutrinos gain an effective mass as they interact with electrons leaving the Sun and then become V1. To consider the math behind neutrino oscillations, it is useful to limit ourselves to only two flavors, the electron neutrino and the muon neutrino. You can express their superposition as being between two mass eigenstates, V1 and V2, being a generalized superposition state. We can then call theta over 2 the mixing angle. If the mixing angle is small, we see the relationship between the rest state neutrinos and the mass eigenstates. If we take the electron neutrino and assume it to travel in free space without any interaction, then we can easily write the Schrödinger time evolution of the state. In this case, the energy eigenvalues are determined by the rest masses and the momentum. Since neutrinos travel close to the speed of light, they are highly relativistic, and we can easily find the energy eigenvalues. The reason why we simplify to two flavors is because we can consider spin 1/2 particles and neutrino oscillations to be identical. The equation to find the probability of a spin 1/2 particle spin flipping is the same as the equation to find the probability of a neutrino oscillating to another flavor. The only difference is the change of the energy levels. Since we already know how to calculate the energy eigenvalues, we can easily compute the energy difference. Additionally, we can approximate neutrinos to travel at the speed of light, so we can easily calculate the time it takes for a neutrino to travel from point A to point B, as well as the relativistic momentum, giving us a complete equation to compute the probability of a neutrino changing flavors. There are two things here that should still be confusing: the difference between the masses squared and the value of E. The value of E is fairly simple, as it's the amount of energy carried by a beam of neutrinos. The amount of energy is determined by the source. So for example, solar neutrinos have an energy of approximately 0.3 megaelectronvolts. As for the masses squared, this cuts back to one of the great unknowns about neutrinos. As mentioned, we don't actually know their mass, nor do we know the mass of their mixed states. What we do know is the difference between the square masses of those mixed states. However, because we only know the difference, we don't actually know which mixed neutrino is the heaviest, giving us two possible scenarios for the heaviest neutrino. But we still know the difference, and that's all we need for our probability. For our example, the square difference between the masses is approximately 8 times 10 to the negative fifth electron volts divided by the speed of light to the fourth. The last thing we want to know is the probability of the flip, usually found experimentally. For our example, we know that a third of solar electron neutrinos oscillate away. With this information, we can solve for our only remaining unknown, the mixing angle theta. We now have a fairly complete picture of the concepts as well as the math behind neutrino oscillations.
Okay, so now that Du has talked about neutrino oscillation, I want to talk about kind of a question that you may be asking is, well, how can neutrinos exactly oscillate to higher mass? This feels like it should violate some mass energy conservation or something like this. So, for example, a muon neutrino going to a tau neutrino. Well, first, let's review how neutrinos are kind of formed. And maybe this is not review, but the only thing I want to touch on is the charged current interaction. So if we take a muon and this interacts with a positive W boson, we will get a muon neutrino, and the same case for the anti-muon neutrino. Okay. And so here I've just have a standard model. I'm just pointing at this W boson. This the Z and W boson mediate the weak force. And the kind of thing to pay attention here with the W boson is the plus or minus 1 charge, because if we interact with positive W bosons here, so negative muon with positive boson, we'll see that because the muon has negative 1 charge, boson has plus 1 charge, we will end up at the desired 0 charge here, okay? So the main meat of what I really want to talk about is, maybe a basis in a Hilbert space. Okay? We know in Hilbert spaces, which is where we are representing all of these different kind of states, like spin states and position states and these kind of things, we can construct bases for different observables, right? So there exists a Hermitian operator that corresponds with some observable quantity. So here I'm saying that we're going to construct this flavor operator, this Hermitian operator F, that has eigenvalues of E, mu, and tau corresponding to the electron, muon, and tau. Excuse me. So, of course, we can also create a mass basis, but this is not what I'm going to talk about today. Not really important, I would say. The main thing is this is a Hermitian operator, so we can construct a basis because it's diagonalizable in its own basis. So we have this flavor basis. Okay. Well, how can we represent the flavor of a neutrino in terms of the mass basis? As you've kind of seen up until this point, we've been talking about the flavor of a neutrino is a superposition between these mass states. And kind of written maybe more detailed is we have some flavor state L. This is equal to the superposition of these mass eigenstates I. From this slide onward, I will probably use M sub I instead of just I. And this out front is something called the PMNS matrix that tells this mass state kind of the mixing angles and how neutrinos evolve and kind of things like this. Okay, so let's maybe have that in writing. So we have this flavor state where the eigenvalues are the electron, the muon, and the tau, and then we have this mass eigenstate I, of which I'm going to write as this from now on, so it's less confusing. We'll have a lot of I's flying around, so I don't want to have anything confusing. So we'll have this M sub I, which is simply the mass eigenstate. The important thing is the PMNS matrix, which is the Pontecorvo Maki Nakagawa Sakata matrix. That's my attempt at pronouncing that. Yeah, okay. So something very important is that it's unitary. And so I put at the bottom, unitary is U dagger, or excuse me, U dagger is equal to U dagger U, which is the identity. All right. And so what the PMNS matrix does, this guy right here, without the star sometimes, doesn't particularly matter. It contains information about mixing angles, as you may have seen in McIntyre's book. And the important thing is how neutrinos oscillate. All right. So these entries are usually determined experimentally, since mixing angles aren't really predictable theoretically. So I thought I would add that in there. With kind of those out of the line, or out of the way, let's kind of talk about more of the math here. So suppose we have some mass eigenstate and we want to act on it with some time-dependent Hamiltonian. I'll talk about that more in a second. Well, then from the eigenvalue equation, we know that the Hamiltonian acting on some eigenstate is simply the eigenvalue corresponding to that eigenstate like so. And so what this implies is that if we want some time evolution of this, right? If we want to evolve this over time, imagine this is psi of 0, and we want to have psi of t here, we can just simply multiply by the e to the power that is quite familiar to you, right? Negative I ht. Maybe not so familiar because you're used to seeing this in the form negative I times some eigenvalue t over h bar. Well, the h bar is still there. I've set it equal to 1 because that's typical in the literature. But this h, the reason this isn't an eigenvalue is because this Hamiltonian actually depends on time. We're using a time-dependent Hamiltonian here, and that's very important to note because we haven't dealt with that in class. And so all I'm going to say is that this Hamiltonian, the energies and the eigenvalues, will depend on time. Okay? So recall the representation of a flavor state in terms of mass eigenstates. So I've written it simply here, and this symbol means corresponds to. That's the flavor state is equal to what we've seen before. Okay, so the PMNS matrix times the mass eigenstate. Well, then we can kind of apply this time evolution operator of sorts, right? We have this Hamiltonian, so I'll consider this whole thing to be an operator, time evolution operator, to the flavor state. And so that would be the sum, the superposition of the PMNS matrix times the mass eigenstates with this time evolution operator out front. And you'll notice we've actually stuck in the eigenvalue this time. We have a specific a kind of steady state, it's called, right? All right, well, what's going on with that? Because we need to realize that the flavor state may change over time, but in reality, the mass eigenstate doesn't change over time, okay? So the mass, we're conserving mass here. The mass does not change over time in the Hilbert space, okay? So these eigenstates correspond to the same observable is the mass eigenstate. This mass is, not changing here, okay? So that's what I'm getting at with this. Well, let's recall some two important things here for the next page, which is rather dense. The flavor state is given is equal to the PMNS matrix times the mass eigenstate. So what that means, because this PMNS matrix is unitary, that we just simply have U dagger flavor state is equal to the mass eigenstate. Okay, so remember these two. I'll come back, but remember. All right. So if we want to represent this, right, we can substitute these two onto either side, right? And we'll get something that looks like this. So we'll have the time evolution operator, PMNS matrix, excuse me. So we'll have the time evolution operator times the flavor state, which is simply the PMNS matrix times the mass eigenstate. And this is equal to the time evolution operator times the PMNS matrix, of course, times the mass eigenstate. But we found here that the mass eigenstate is simply the U dagger flavor state. So, this summation that you saw previously up here, this summation is implicit right here. I just want to make note of this. The summation is implicit on this line, all right? And so this is equal to, because U is unitary, so we can cancel these, this is equal to the summation from 1 to 3 of the time evolution operator with a specific eigenvalue, okay, it's not time dependent up here, times the flavor state. So this is kind of our takeaway. And since the PMNS matrix tells us how a neutrino oscillates, we can see that the result doesn't actually oscillate. So the flavor state doesn't oscillate over time, okay, since the PMNS matrix is not present. Well, what that tells us is that the Hermitian flavor operator, F, as we discussed earlier, doesn't actually commute with the Hamiltonian, right? So we have this time evolution operator with this Hamiltonian up here, in this case, a specific eigenvalue, but this does not commute with the flavor operator, okay? So the flavor operator does not commute. I've kind of written that mathematically here. The commutator of F and H is non-zero, and so in the literature this is usually given as e to the matrix power here. There's a good pre-blue one brown video on this that you can watch. So all right, well, let's see kind of, so what, this flavor state is not oscillating. What does this tell us about why it can oscillate to higher mass states? Well, so we know that the flavor state isn't oscillating here. That's what this tells us, Okay, the PMNS matrix is not, not present, so there's no oscillation of the flavors. And so what that tells us is that since we're looking at a specific mass eigenstate, it cannot be the case that neutrino flavor oscillation depends on specific mass energy or mass, right? And so I put here that it depends on the difference of mass, not the mass itself. And so our conclusion that we kind of walk away with here is that the oscillation of neutrinos does not depend on the mass energy of neutrinos. And so maybe an electron neutrino has less mass energy than a tau neutrino, but it still can oscillate to the tau neutrino because the oscillation is completely invariant or does not depend on the mass energy of the neutrino. Okay, so I've written something here as well. I've just written that if we apply this flavor operator to this time-dependent operator and all of this to the flavor states, this is actually not equal to this here. Okay, so it does not commute, and we cannot use the eigenvalue equation as we did at first. And so here's the references for part 1. Here's the references for part 2, and here's the references I used for part 3. So hopefully that all made sense, and yeah, thank you.